Thank you everyone for tuning into today's webinar. Our speaker is Dr. Mark Bentum from the Eindhoven University of Technology in the Netherlands. He'll be introducing what sounds to be a very impressive lunar constellation of small satellites for radio astronomy. So Dr. Bentum, please go ahead when you're ready.
Yeah, thanks a lot, and also thanks for the invitation. I think you see my screen right now. Just to acknowledge. Yes, okay. So today I'm going to talk about, I think it's a very catchy title, Flying to the Moon for Radio Astronomy at Low Frequencies. And yeah, you can see an artist's impression of what we are aiming for. And today I will talk a little bit about what our goals are and why we want to go to the moon. Actually, we are there already, but to extend that. So you can see I have two affiliations. I'm working at Eindhoven University of Technology, where I'm a professor in radio science. I also put it on this slide. I'm also working for Astron, which is an organization, a governmental organization in the Netherlands, and I'm their head of the astronomy and operations group. And here you can see a little bit of the work we are working on, or I'm personally working on. It's all about astronomy, and that's also where my interests are, how to make radio astronomy possible. Now here on this image you can see a couple of very interesting pictures from astronomy. We'll not go into detail, but these are, although they are beautiful, these are all optical images. So images made by, in general, by the Hubble Space Telescope, all three of them, if I'm correct. And that's not what we are aiming for. We are aiming for radio astronomy. So for frequencies in the radio domain, and we're talking about frequencies of a couple of hundred kilohertz all the way up to a couple of tens of gigahertz. That is the interest of, in general, of radio astronomy. And why should we do that? Why is astronomy interesting? For first, it has very beautiful images, of course, but there are also some big questions which we want to solve in astronomy. And one of them is, for instance, what is dark matter? And we know that if you take the universe and you calculate what would be the part of normal matter, chairs and stars and things you can see, and some of them you can even touch. That's only 4% of the matter. From calculations and observations, we know that at this moment, and this graph can change in due time, that 21% of all the stuff in the universe is dark matter. It is matter, but we cannot see it. And 4% is normal matter. And then about 3/4 of all the things in the universe is accounted for as dark energy. And that is the second question, which we in general, but specifically we as well, want to have answers to. Then the third question, the third biggest questions about this at this moment in the universe is, we know that the universe is expanding. We can measure that. It's actually very easy to measure it. You just look at radiating sources, and what you see is, because we are expanding at a tremendous speed, that the signatures in the frequency domain changes due to the Doppler effect, which is caused by the expansion of the universe. And therefore, if you calculate back, it has to start with something we call now the Big Bang. And there's in the picture on the bottom, on the left side, you can see in colors, nice colors, the whole evolution of the universe, and that's interesting. And the big question is, what came before that? We probably will never have answers to that, but nevertheless, it's an interesting question. The fourth question is what's inside the black hole. As you can see on the screen, we know a little bit about black holes. We know more and more about black holes thanks to radio astronomy. Actually, the picture of M81 of the black hole there is done using radio telescopes at very high frequency, by the way. Not what I'm going to discuss today, but it's radio astronomy. And the last question, the biggest questions, is are we alone? And the big question is, how can we answer those questions? And there astronomy comes in. Astronomy is just measuring. It's just measuring in the lab, and the lab is in this case our universe. And how can we do that? Now we can do that by making images. Here you can, if you have a very good eye and you travel all around the globe, this is what you see at various places. You can see a big, what is it? A line in the universe. This line is not there because it's particularly bright in the middle of the universe as we see it in our position, but it's simply because you see our own Milky Way, and it's just closer by than all the other Milky Ways you can see on this picture. Now, this is an image in visible light, and you are able to see it if it's a clear night. Of course, there are other frequency bands as well where you can look at. You can look at gamma ray, you can look at X-rays, ultraviolet. By the way, all three of those should be done using satellites, because you have to go outside our ionosphere. Now, infrared is very famous. There are also some satellites, by the way, doing that. Microwave and main radio. And then at the lower right, you see a very, how can I say it? Very not clear. There's not a lot of information on it, and we call that low frequency radio. And our aim, or the aim of the team I'm leading, is to make a better image and do science, of course, on low frequency radio. And an interesting question might pop up in your head right now is, why is that image not filled in more accurately? And then I hope to give you some information about today why that isn't the case. And of course, the idea is, what can I tell you to make that nice picture, like for instance, in main radio or even invisible for low frequency radio in the future. Of course, there are also sounds from space. A couple of them, not too fast, is the background. I hope you can hear this. It's just noise. It's the galactic background, which we can sample. You can also sample pulsars. The Crab pulsar, as I hope you can hear this, but or a pulsar with a very sexy name, BO329, or the Vela cluster, very popular due to a couple of movies. Now, those signals, we can transfer them to sounds, and that are also placed, or you can also discover that in using telescope. Oh, I will not do this one today. So how to capture the signal, how to do your lab experiment, as I said, in the big universe. Now, first of all, you have to notice a couple of things. First of all is that if we draw a line from wavelength, or the other way around is of course frequency, as function of opacity of the atmosphere, we see that at say high frequencies or small wavelengths, nothing will come through our atmosphere. Therefore, gamma rays, X-rays, ultraviolet signals, you have to go outside the atmosphere or going into space to detect them. That's the reason why we have gamma rays, satellites, X-ray satellites, and even ultraviolet. As you can see in the visible light, there is some low opacity, or it's transparent. Fortunately, else Earth will be very cold. So we can do observations. We can sample the universe in the visible light. At millimeter wavelengths, things are over again. So it's completely opaque. It's not transparent. Transparency is the inverse of the opaqueness. And in the radio, hey, that's interesting, it's completely transparent. Therefore, you see radio telescopes on Earth. You can monitor the universe at radio frequency quite well. Except at a certain moment, this line is not very sharp, and it's changed in a day to night manner. But at meters wavelength, at tens of meters, still 100 meters, then the universe will be completely opaque again. Now, and the image I showed you is in this region. A little bit about this region. So that means that we simply cannot observe that from Earth. You need to have a space-based system. Okay. Now, some pictures will always do good in presentations. Here we see a couple of telescopes in Hawaii. Those are optical. But we also have radio telescopes all over the globe. In the background, you see a radio telescope array. It's a linear array, by the way, in the Netherlands. But also in the US, you have the Green Bank telescope. It's somewhat more than 100 meters in diameter. These ones in the background are 25 meters in diameter. The Evelsberg telescope is also about 100 meters in diameter in Europe. And here we see a former picture of the Arecibo telescope in Puerto Rico. Fortunately, last year it's crashed completely, and it's not there anymore. Now there is some crashing remnants of the telescope, unfortunately. This one was 300 meters in diameter. And then we have, I don't have a picture of that, but the largest single dish telescope on our Earth surface is in China. It's the FOSS telescope, and it has a diameter of 500 meters in diameter. So today I will not talk about those big dishes. I will talk about a technique we use, aperture arrays, in which we make antennas, like you can see here on the spot. Antennas which are very easy, simple antennas, easy to make. They are not movable anymore. They are just stick to the ground, so they are much cheaper. Unfortunately, the area, the sensitive area for the recipe or the receptions of signals is less as well, and therefore you need a lot of them, and I mean a lot. Here, in the upper right picture, you see an aerial picture of a LOFAR. It's a low frequency array we've built in Europe, with the center point in the Netherlands, and we have approximately 100,000 of the antennas working together as one big telescope. And I will also say something about how we will do that in space. So the principle of an aperture array is quite simple. On the right you see a simple or a standard radio telescope. There's a nice reflector, a parabolic reflector, and the waves are coming in, whether it's from a dark matter signal or from a Milky Way or galaxy or from a pulsar or from something else, from life elsewhere, who knows? It's coming in, it's reflecting on the parabolic surface, and there's a coherent addition of the signals in the receiver. So you need one receiver for one parabolic dish, but effectively the size of this, the electromagnetic size and the aperture, which is approximately 70 to 80% of the size of the parabolic itself, is sensitive to a specific place at the universe. And if you want to say to look somewhere else, you just move your telescope around. A very expensive mechanical structure. Now, what you can also do is flatten it and have a lot of receivers. So no reflecting object, but just a lot of receivers, all have an amplifier, and they have a delay. And why we have a delay? It's simply because if a wave is coming from the wave of interest is dropping on our aperture array, it will receive a little bit earlier on this antenna than that antenna, and you have to compensate for that, and you do that by an artificial delay here, which is exactly the same as a physical delay in reality. And you do that for all receiving elements. You add them up, or you combine them at least, and we have more sophisticated techniques for doing that, and you end up with a similar image as you would end up with a parabolic reflector. It's even better. Now, the good thing is, of course, with a aperture array, you just, although it's impossible in time, but if you wait a little bit, you can add a different delay, and you look at a different position. Or, even more, you duplicate your digital hardware, and you can look at 2 directions, or 8, or 10, or 1,000 directions at the same time. So as you can see, aperture arrays are way more sophisticated than parabolic techniques. Of course, the challenges are not in the antennas anymore. not in the LNAs, they are in the post-processing here, in the signal processing part. It's not a new idea. Already before Christmas, they used the electromagnetic waves, in this case sunlight, is nicely reflected by mirrors, and just added up here nicely in the boat, and the rest is history. Also in astronomy, actually, this is the discovery of radio astronomy. This person here on this plate is Karl Jansky. He had a specific task at Bell Labs in the US by looking at radio waves. But what he did, he made a phased array. You see here the antennas. It's a 2x4 antenna, and he used that to calculate directions of transatlantic radio communication signals. Unfortunately, for him at that moment, unfortunately, he saw some changes in the signal on a day-to-day basis. Eventually, it was the discovery of a signal out of space. So the first radio astronomy experiment was done in the late 30s of the last century with a phased array. And also the discovery of pulsars by Jocelyn Bell in Cambridge, you can see over here, was done by, in the pictures, by a phased array antenna system. So actually, phased arrays or flat antennas, or there are many names, aperture arrays are many names for that, were the first real the use of arrays of antenna systems in astronomy. However, if you Google radio telescopes, this is what you end up. Dish, all dishes. And even today, I don't know when I made this image, a couple of or a year ago or so. But still, if you do that today, radio telescopes, you end up with dishes. So we are not there yet. But we see that there is a new revival at this moment of aperture arrays. And you see a couple of examples here. This in the upper left part, it's called LOFAR. It's a low frequency array in the Netherlands. Here we see an artist's impression of SKA, the square kilometer array in South Africa. Here we see an artist's impression of the SKA actually also in South Africa. But we're also building part of the SKA, the square kilometer array in Australia. And here you see an experiment. I will not go into details to that. You see a dish, but in the focus box of the dish, and you see this part, there's also a phased array. We have 121 elements placed in the focal plane of the antenna. We call this also a focal plane array. So there is a revival at this moment. And there is a reason for that. I'm not using a lot of equations today, but here we have one. This is a sensitivity, the opening angle of your telescope. That means the smaller this number is, the more detail you will find in space. And that's depending on the wavelength over the diameter of your aperture, the diameter of your telescope. And you will see, and I said the smaller this number is, the more detail you can see. So if you want more detail, if you don't want to see 1 pixel with a galaxy far away, but you want to see the details, yeah, you need a smaller number here. And you can do that in 2 ways. You can go to higher frequencies and therefore smaller wavelength, or you can increase the dimensions of your system. Now, wavelength is also giving us information about the content of the signal, so that's not a thing you really want to work on. What you really want to do is make larger telescopes, hundreds of kilometers perhaps. Or thousands of kilometers. But that is a little bit difficult to make in a single parabolic system. And therefore, aperture arrays coming into place. And that's also what we do. And one of the largest examples on Earth is the LOFAR telescope. Here you can see an impression of our antenna. Now, I don't know how you see it, but I think it's not very spectacular. It's just a wire antenna. Actually, the wires are the antenna. Here in the top, there's a low noise amplifier to amplify the systems. But we have hundreds of thousands of those antennas spread it out over Europe. Here you've seen, by the way, an artist impression. So this is the Netherlands, this is the UK. We also have Denmark here and Sweden, the Germany is here and France. And we placed at this moment in time these kind of antennas in Ireland, the UK, in Latvia, France, Germany, Poland, Sweden, and we are aiming for Italy and Bulgaria as well. So that means the size of Europe. It's about a 2,000 kilometer sized radio telescope. And if I go back to this formula, you understand why we do this. Because we want to have more detail from the signals out of space. We want to see if matter around a black hole is really moving. Because if it's moving, we know, and we cannot see the black hole, of course, we can detect that black hole as an example. Or we can do some spectroscopy about a specific planet. But we need to see the planet, not to see a whole solar system. So we need to have smaller values of this data here. And therefore, and the only way to work with that is going to larger telescopes. So that's the reason why we built LOFAR. And you have a small impression, so some antenna systems and etc. So if you look at an aperture array, what it's consisting of, now I already told you, lots of antennas. That also means a lot of low noise amplifiers, lots of receiver systems, and with all these signals, we can do, for instance, make a beam on the sky, or we can make an image of the whole sky, and that's done by what we call an interferometer. So here an impression, just for because the images are nice. You also see the impression of our country a little bit. It's flat. And here we have what we call a high band antenna for somewhat higher frequencies. And we made some hardware ourselves to do so. This LOFAR, as I didn't told you, but you can see it. I go back one. And the high band antenna, the upper frequency is 270 megahertz. What you see now in the development of aperture arrays, that we are going to higher frequencies. So, for instance, the MWA and LWA are at high frequencies. Actually, we are wanted to go to about 2-3 gigahertz aperture arrays, and that's also where at Astron as well as at the TUI we are working on techniques to make that happen. Let's skip this one for now. The thing though is going to higher frequencies. It is possible. It is challenging because the higher your operating frequency, the smaller your antennas will be, the smaller your aperture, your effective antenna aperture, so the sensitivity more or less of your antenna will be, and therefore more antennas you will need. And you end up, if you go to very high frequencies, that your number of antennas will go up almost impossibly. And with that, also low noise amplifiers and your post-processing, signal processing part will be very, very, very challenging. Going to lower frequencies, there are other issues. And that's what I'm talking about now. And there we also come to our space-based system. So till approximately 30 megahertz, so from 30 megahertz upwards, we can do our observations on Earth with our LOFAR system. But below that boundary, it's not really a hard boundary, so therefore I say approximately 30 megahertz, things are becoming extremely difficult. And there are two reasons for that. One of the reasons is our ionosphere. To give you an idea, this movie you see now running it's made by the Very Large Array, and we are looking at a galaxy that's in the middle here of this movie as function of time. Now, we only used a couple of antennas at the VLA in the US. That means that we undersample our system. Therefore, you see all the lines in this image. But the rotation is due to time, because our planet is moving, and therefore it's rotating. But what you now also see is that it is moving. Actually, our point of interest, that's a galaxy I mentioned here in the beginning, it's even out of our image. And that's not because the antenna system itself is moving. It's fortunately also not because the Earth is shivering. It is because the ionosphere, and especially the layers between 100 kilometers till about 1,000 kilometers from the surface of the Earth, is impacting the electromagnetic signals. If I give public lectures, I always say you have to compare it with a swimming pool. If on a cloudless day, if you look up, you see a blue sky and you see the sun. But if you dive into a swimming pool and you lay on the bottom of the swimming pool and you look up, what you see is not only the sun, but you see shining lights everywhere. And that is because of the surface of the swimming pool, because you jump into the swimming pool, so they're all little waves, and they are reflecting and diffracting the signals. And that's exactly what the ionosphere is also doing at low frequencies. And this, to give you an example, is an image or a movie actually on 74 megahertz. If you go lower in frequency, it's becoming worse and worse and worse, and you cannot actually measure anymore. By the way, what you saw in the image, and you can also see this in the graph, is that it is reasonably quiet, and then at a certain moment it's becoming wild. The edge wild that the galaxy is out of the image. That's the moment when the sun is coming up. It's sunset, and the sun impacts our ionosphere. Now, if you go at frequencies below 10, 20 megahertz, there's a complete shutdown of signals from outer space. You cannot even measure anything. And there's a cutoff frequency, which is depending on the activities of the sun, but nevertheless, it's around 10, 15 megahertz. There's another reason why we cannot do this on Earth. That is because those frequencies below 30 megahertz are used a lot to other purposes. For instance, for communications. Now, you can see it here a little bit on this graph. I think I will not explain everything due time, but this is the most interesting one. This is a recording of the Radio Astronomy Explorer, the second one, B, already in 73 last century. It's a lunar orbit, and what you see is there's a satellite at different frequencies, and 250 kilohertz, 360 kilohertz, all the way up to 11 megahertz, is orbiting the moon, and it will only signal, it's one antenna, it will only signal the signal strength. And what you see here is, let's make this 480 kilohertz signal. You see some signal here, it's becoming a little more strong, and then at a certain point it's gone. Now this is because here the satellite is facing the Earth. It gets some signals from Earth. The antenna is rotating a little bit, so the signal strength will vary as well. And then when the moon is blocking the line of sight between the Earth and the antenna system, it's a flat line, and then it's opening up again. So we also know by this measurement that the Earth is the problem. Now, being on Earth, it's even more problemsome. We also made an image with LOFAR. This is a 15 megahertz image of LOFAR, which you can see there are no details of the universe, but you see some very strong signals here. These happen to be, I think this one was a radio clock signal, DTS, about 500 kilometers from our side. And this very bright one here is our own power supply. So we had to have a mobile power supply, so a generator, and it generates a lot of interference, including interference we measure ourselves. Okay, so we have to go out of space. And why is that interesting? Now, there are a number of reasons. I will explain, and of course, beautiful pictures. I'll explain two interesting ones. First of all, it's exoplanets. Exoplanets are planets which are not in our solar system. They are they are far away from our own solar system. It happened to be that if a planet, if it's magnetized and it interacts with solar mass ejections, CMEs or solar winds as we call it, there are bursts generated. We know that because we have a very big magnetized planet in our own solar system besides the Earth. It's Jupiter, and Jupiter emissions are very, very clearly visible at somewhat higher frequencies, about 30, 40 megahertz. And we already discovered that in the 60s of last century. So it would be fun to look at the universe and see if those low frequency signals, Jupiter was about 30 megahertz, most planets will be much, much lower. To give you an idea, the Earth also generates pulses. We cannot see them because our ionosphere is blocking them. But if you go outside, far away, and you watch the Earth, you see that this interaction of our magnetic field with those signals from the sun, those solar winds, is about 1 to 2 megahertz. And yeah, we wanted to look, and that was one of the main questions of astronomy. Is there life outside? Now, that begins with the detection of an Earth-like planet. And this might be interesting. So low frequencies, you might detect exoplanets. And we didn't saw them up till now because the most interesting planets are below the cutoff of the ionosphere. The other very interesting topic is the dark ages. I have to explain a little bit more. It is here we see on this image, we see the timeline of our universe. And that starts with the Big Bang. I already told you, and probably you know that, is that the universe is expanding, so it's becoming bigger and bigger and bigger. And here we, at the right side, we see our current status of the universe. Of course, from the Big Bang all the way up to the current status of the universe, things are happening. And what we do know is by observations, radio astronomy observations, that at a certain point you can measure the universe. Then light, electromagnetic waves, and also heat can be no heat not, but electromagnetic waves can transport, can propagate at the universe, and we can detect that. The thing, though, is that the universe is expanding, and therefore the signals, which were very high frequency signals, will go down in frequency, and we can observe that at lower frequency. Now, what we also know is that at around this time, there are no stars, so it's dark. That's also the reason why we call it the dark ages. And at a certain point, matter will clutter. And actually, matter is able to radiate. Now, what is the most present atom in the universe? That is, of course, hydrogen. And we know from experiments from Earth as well that the spin moment of hydrogen, where we swap the moment of the electron, radiates at 1.4 gigahertz. Actually, we made atomic clocks based on hydrogen at 1.4 gigahertz, 1420 megahertz. We hope, that's our hope, we didn't do that yet, is that we know it should happen in the dark ages as well, until a moment when there's a lot of this stuff around and we can see structure in the universe. And we hope that this 1420 gigahertz signal is still observable. However, the universe is expanding, and therefore this 1420 megahertz signal will drop down substantially because it has been a while and the expansion is going on and on and on. And we think that those signals the signals where we can have an impression of the structure in the dark ages, so the start of the formation of the universe as we know it today, will be signals around, here's the big question, when? We are not sure yet. Is it 5 megahertz? Is it higher in frequency? We don't know. We estimate it, and we estimate that we can see a signal like this. And especially here at around 10, 15, 5 megahertz, we hope to see a signal which proves the existence of hydrogen in the dark ages. And what are the structures? What can we learn from that? And this is Nobel Prize winning science. But unfortunately, and I hope I make that clear to you at this moment in my presentation, we cannot observe that from Earth. The ionosphere, as well as the interference, is preventing us from making observations. And therefore, the only option is to go into space. Now, I made for completeness a list of what you can do with low frequency radio astronomy. I wrote a roadmap on this as well, so you can read that in one of my papers. But the main things are exoplanets and the mapping of the very early universe, what we call the dark ages. This is the current status of that image at low frequency. It's done by probe again, the Radio Astronomy Explorer, done a while ago, and this is a very inaccurate image, but promising, because what we see is we see lines here. That means that they are at the same strength, that something here is present. So we know there is structure at low frequencies. So that's promising. So let's make a real image. And the strawman design of the things you can do is actually we see there are many options, but we foresee 2 main options. One of them is the expensive one, building a site on the far side of the moon, where if there is interference from Earth, including that burst-like signal from the interaction of magnetic field and the signals from the sun, go on the far side of the moon. That's a moon-based, very expensive one, or make a space-based system. And what we are doing, we do both. We are aiming for a space-based system at the medium time interval, say within 10 years, and the moon-based systems afterwards. Actually, we are involved at this moment in an ESA, European Space Agency, how you call it, a study on going to the moon. So, but that's not going to help us in the upcoming 10 years. So we are aiming for what we call OLFAR, an orbiting low-frequency antennas for radio astronomy. Now, radio astronomy, I told you a lot about. Low frequency, now we are going to orbit somewhere from. And this is also our idea. So our principal idea, and I will show you a small movie in a minute, is we built a lot of antennas. We did the math here at this image. You see 50, but if you really ask me to give an honest answer about how many satellites you need, we are aiming for hundreds of satellites. And there are 2 reasons for that. One of them, you just need sensitivity, you just need number of antennas, you just need aperture for it. And the second one is we want to see details. We don't want to make the same image as the Radio Astronomy Explorer did in the 70s of last century. We want to have detailed images, and that means that the swarm should be really big. We're talking about hundreds of kilometers in diameter. Of course, we need to make an antenna. Now, for those who followed a antenna course on the university, or for curiosity, know that the frequency depends also, or actually the wavelength, I have to say, makes the size of the antenna. Yeah, unfortunately, we are aiming for very high, long wavelengths. So that means that the antennas are very, very big, and they need to be deployable in that sense. Of course, and there are a couple of other things. We need to communicate between the satellites. Power is an issue, so we need solar cells to get at least some power. But yeah, we need it for various applications. we need to be autonomous. We cannot have a control system which controls hundreds of satellites. They should actually operate on their own, which, by the way, is good. And for the downlink, I will say a couple of words on that. We need special techniques. Now, what is the concept? I show you that in this animation. It's unfortunately not for real. Also, there are some issues with sizes. So we have the Earth here, we have the Moon here, and the idea is to orbit around the Moon in this greenish orbit. And you can see that this reddish part, it's the zone where we can do the measurements. Because if there are some interference from Earth, this zone will be blocked by the Moon itself. So therefore, this is the part where we can do the observations. Now, as an example, we can look for a 200-kilometer altitude. So we're flying nicely around the Moon. Looks a little bit like Space Invaders. Here we have, as an example, 6 satellites with some solar cells, and they fly around in different orbits, not hitting each other. That is, we should prevent that. But also what you see is that the orientation changes with respect to the universe. And that's exactly what we want. Yeah? So we are working with distances between satellites and the orientations of that line between satellites to do our imaging. Now, if we face the Earth, so if we are not in that ready zone, we do the downlink. So the data we captured during the measuring phase, we send to Earth again until the moment that the Moon is blocking the interference signals from Earth, and then we do our measurements. And what you see is that our instrument, in this example, consisting of 6 satellites, we're ending up to hundreds of satellites, will form, like LOFAR on Earth, form a telescope consisting of hundreds of individual antennas, all the way up to one big telescope of, say, 200 kilometers in diameter. This is the same principle. It's aperture, an aperture array. It's not two-dimensional as it is on Earth. It's really three-dimensional. That's also the challenges. And here we are aiming to make the telescope to observe at low frequencies. Now, you see the Moon as an example. Of course, the universe is very big, so there might be other locations as well. Of course, there are some considerations for picking the choice. We need to do the science. We need to make the picture of the dark ages, and we want to detect exoplanet signals, and we want to see if there are Earth-like planets in the universe. We have to deal with the interference from Earth. Also, the stability of the orbit is really important. And of course, what also is important is that the further away you go from Earth, the more energy you need to transfer the data, and also to control the swarm, by the way, but to transfer the data from the swarm towards Earth. So also be as close to Earth as possible, but checking all the boxes here. So there are a couple of orbits. You can see a list here. There might be more, and you can also go to Mars as an example. It's even more expensive. So on top, what is our ideal is to go to the Moon. At the Moon surface, at the far side, there's almost to no interference. But it's very expensive to go on the Moon to build a system on the surface. A logical step would be a Moon orbit. The disadvantage of the Moon orbit that it's not as stable as we wanted, and also lifetime is limited. So we're also considering what we call a dynamic solar orbit. So just depicted here in this graph. This is the Sun, this is the Earth, this is the Moon, and there are a couple of stable or almost stable points. L2 is a famous one where a lot of scientific satellites are placed. The Earth is on a very stable orbit, fortunately. And what we can do is that we can either go, if this is the orbit, we go in front of the Earth in a orbit which is almost equal to the Earth, or we trail the Earth. So that's another consideration of where we can place the swarm. And of course, then there is no blocking object like it is if we use the moon. So we should go far, far away from the Earth, and we're thinking about 5 million kilometers. So therefore, the moon is a more feasible option at this moment in time. But we are considering the other options as well. Now, just a couple of remarks about the radio architecture. Actually, it's very simple. You're having a low frequency antenna. We receive, we sample the data. We do some communication between the satellites, also for control, but also for data processing, and we send the signals to Earth. It's not really spectacular. It's the application which makes it spectacular. So to give you an idea, we are aiming for small, of course, the smaller the satellites, the better it is, because we need a lot of satellites. So we're aiming for CubeSat-like satellites, for instance, a 3U or a 6U one. And now for the antenna, one of the options we look for is very primitive sketch here, that at the edges of a CubeSat, so we're adding for a couple of centimeters of thickness, where we have 1, 2, 3 just parts of a monopole, and at the other edge of the CubeSat we also erect 1, 2, 3 antennas, which have a length of about 5 meters each. And this is a first prototype. So we print it completely. We have a plastic where in the center there is a conductor which acts as the antenna, and we just nicely roll it up in one container with a couple of centimeters high. And when we're on the spot, for instance, around the moon, we eject it, and 5 meters of plastic will come out, and will form. We have 2 of them, and together they form 3 dipoles, which can sample the complete 3D environment. For the downlink, just one slide. What we can do is making a modest satellite, but one of our design criteria was autonomous operation, and therefore we are aiming for that each of the satellites with the long antennas on it will cooperate communications down to a base station on Earth to give it away. And then here we see an example of our satellite, and the 3U satellite with the long antennas. They are they are 5 meters each, of actually 5 meter tip, and we have solar panels for powering, and at the other side of the solar panel we make, here I showed it with my pointer, we make that antenna system for the downlink to Earth. And actually, here it is. Sorry. And we already made a prototype of that. So one part we made solar panel, and the other part we made a very rudimental antenna with only 3 patches. We have to do somewhat more clever, but to give the idea that we can integrate antenna and solar panels in the same part. Now, what are we doing at this moment? A long list of things we are working on. Working on the computer, we are working on timing, for instance, what kind of clock you need to have. Thinking about chip-like clocks. Now we're working on that as well. Propulsion. Now we wrote a roadmap, and so the point at the horizon. Actually, the point would be a moon-based system, but the second point on the horizon is an orbiting system consisting of satellites, perhaps hundreds, at least, perhaps thousands of antennas. So we are working on that, but we have a roadmap. So, and here are some projects we worked on, and we finished actually. So we started with a conceptual program. We call that DARIS, which was paid by ESA. The OVA project, which is our vision, and a couple of others. And the last one we really realized is the NCLA. A couple of words on that. It's called the Netherlands-China Low Frequency Explorer. It is in space right now. It's a Chang'e 4 satellite, and on the satellite I always say we duct taped our antenna system. So what is the mission itself? It's already in operation for a couple of years. And we have the Earth, we have the Moon. And what was the purpose of this mission is to put a rover on the far side. Of course, not us, the Chinese. The rover needs to communicate, so they put a relay satellite in the Earth Moon Lagrange point 2, which is about, as you can see in the picture as well, 64,000 kilometers behind the Moon. There's I don't know if they fly in a circle or an ellipse, or they made a nice 8 or so, but at least the satellite, this relay satellite can face the Earth, but also face the signals of the rover on the Moon. Now, we placed a payload on this relay satellite. For the reasons are to operate between 80 kilohertz and 80 megahertz, so we extended our high frequency bound a little bit to get information about the solar burst. So our concept of exoplanets, we test that on Earth and on Jupiter, of course, and also we hope to see something about signals of the dark ages. Here you can see an artist's impression. You see the Chang'e 4 satellite and big box, big solar panels, a big parabolic antennae for the communication to Earth and of course also to the Moon. And here you see the payload with 3 long antennas. They are 5 meters each. And it's actually very big. It's not CubeSat-like design. We had a lot of space here, and we already also did that. Now, our initial design, we thought it would be easy, just a commercial off-the-shelf system. Now, we ended up with a problem, and the problem was EMC. So it resulted that the Chang'e 4 satellite was extremely noisy at low frequencies. For instance, by power supplies, switched power supplies, and but also other things. And so we had to cope with that. So what we did is we didn't use commercial off-the-shelf stuff. We developed our own LNAs with a huge dynamic range that we can cope with the EMC as well as detection of the signals we want. And to do so, we had to divide our one LNA in 4 bands. You can see the frequency ranges here. So now here you see an impression of the boards we made. Here we have the LNA board. We also have a connection to the receiver board. We added a calibration source board to calibrate our system. Now, and here you see the flat set test. You can already see that the system is not CubeSat-sized stuff. It's much bigger. It's actually a big box. Now, the current situation is that we have images of our antennas. This is a image of the boom, and the 5-meter boom. Here you can see the inset is of an image before we enrolled the antennas, and here you can see that the boom is really enrolling from that satellite in space, 64,000 kilometers behind the Moon. So we are operational. All the 3 booms are out, not completely. They were stuck at 4 point something meters. So actually, that's for our experiments is even better, because then we aim for somewhat higher frequencies, which we can also look and validate with Earth-based observations. The thing is that we don't have data yet. So the Chinese partner is doing first their experiments, and as soon as they are ready, we get our opportunity to work with the system. So we are hoping that in the remainder of this year we can do a lot of experiments and really do the first steps in low-frequency radio astronomy. Now, what are the next steps? Of course, analyze the data. We really want to do that. The next step is we cannot use this payload in a CubeSat version. We need to make it smaller. So that's what we're working on. We're also working on the antenna systems, because we think, actually, as a PhD student of me, we are thinking that the dipoles are very interesting and easy to make, but they are not really broadband. So we are aiming now for a new type of antennas. We are working on this right now, and our next step is working on a smaller mission, say a couple of CubeSat in moon orbit. Of course, we are also working on rovers on the moon. Just an idea. This is just a fun idea, but we have rovers which can eject an antenna and be sensitive for frequency at low frequency signals. And of course, our roadmap in the end, what we want is an all-far or a base on the far side of the moon. So we're also working on new antenna systems, as like I said here. Much broader frequency, broader antennas than the single dipole. This sinusoid antenna turns out to be giving us at least the best simulations. And but that's you have to imagine that at the low frequency, the diameter is about 10 meters of this antenna. Imagine that, make an antenna connected to a CubeSat, and how to do that, how to be able to get that antenna there and to explode it there, being a 10 meter in diameter antenna. So we are exploring ourselves on inflatable antennas right now. We have some here at the university, some experiments coming up. We have students working on inflatable antennas, and yeah, that's also concepts we want to test. Another concept is by memory memory or smart memory alloys, where we have antennas constructing of metals. What you can do is then squeeze them in, for instance, in 1U of a 3U CubeSat. And as soon as you're on the spot, either in a dynamic solar orbit or orbiting the moon, if you're there, then it's smart memory alloy. It will go back to its original shape again. So that is an option. We are looking at that as well. By the way, this material is not only limited to lines, but you can also have patches. So that might be very interesting. And of course, we're working on integration. And here you can see the first chip we made for the LNAs. It's not back yet, so we don't know if it's working, but it will soon be back from the fab, and then we can see if it's functional for that as well, to make eventually all our electronics as small as possible. All right, so I don't know if I'm okay in time, but the conclusion, so last slide, is we are aiming for radio astronomy experiments, looking for exoplanets, and also looking for the dark ages signals. Might be a number of signals there. We don't know. We think it's Nobel Prize winning science, but to do so, we really have to go outside our ionosphere, so in space, which makes it even more interesting. It is the last wavelength not explored yet. So that might also give us some unknown signals, which might be even more interesting. Now, the reason we have to go, you can see it, and it's the ionospheric blocking of the signals, or at least impacting the signals. And remember my swimming pool experiment, and RFI. That's even a bigger problem, and will become a bigger problem in the future even more. And then we go out to make a big swarm. Hundreds of satellites. We think that technology is ready now, but we have to test that, and that's our next step with OLFAR. And our ultimate goal is really making a moon-based observatory, not only for the low frequencies, by the way, but if you're there anyway, we can also make a very RFI-free observatory at the moon. That, by the way, will be the most expensive one. Okay.
Thank you. It's very impressive, the diverse types of development work that you're doing. May I ask what size your team is?
Yeah, we have a consortium. So we have about 10 people here at TU Eindhoven working on that. We have TU Delft, well known in the world as well. They are not for the payload, they are more on the system, how to organize that. I think they have about 10 people working on that as well. And then the science part, we do that together with Radboud University in Nijmegen, also in the Netherlands. also a whole department actually which working on that, sometimes full-time, sometimes a little bit less. And then we have a huge number of companies are interested in this as well. So yeah, our community is, yeah, I don't know. I think if I write down the names, it comes up to 40, 50 people or so. Yeah.
Wow.
But they
Okay.
are all working full-time on that.
Big questions require big teams.
Yeah.
So, in the case of a phased array, I understand the relative positions of each element in the array is important. So, with regard to your formation flying concept, how important is precise orbit determination for your different CubeSats with the antenna elements? And does this mean that is there some way of doing this autonomously, or will this have to rely on post-processing?
The answer to the last question is post-processing. What we do is we are not really do formation flying. So actually, it doesn't matter where they are, as long as we know where they are. So we want to know the position instead of controlling the position, and that makes it easier because we don't have very expensive and accurate attitude control of our satellites. But we do know to know the position, the localization of the antennas with respect to each other. So actually, in our imaging algorithms, what we need is what we call the baseline. It's the center of one, the phase center of one antenna and the phase center of the other antenna. We want to know the distance as well as the orientation in the three-dimensional system. As long as we know that, then it's okay, and we can do the imaging part we can do in post-processing algorithms.
I see. Okay. Before I ask my next question, I'd just like to remind the audience, if you have a question, please feel free to raise your hand or speak up, or you may also type your question in the chat box. So how important is the attitude of each spacecraft? Do you need very fine attitude control, or?
No, as long as we know it. No,
okay.
As long as we know it. Actually, what we do is we're looking at signals which are not, except for the exoplanet signals, by the way, but for our dark ages application, it's a very static signal. It's there. It will be there for another year. So what we do is we sample it over and over and over again, and we integrate the data. But what we're really doing is we're filling in a sphere, a space, three-dimensional space, where baseline and orientation are put in that space. And what we want to know is all the positions in that space. So as long as the satellites are moving with respect to each other, we get different baselines and different orientations all the time. And they are filling in that three-dimensional space. So actually, the more they move with respect to each other, the better that space will be filled. And in the end, our images will be more accurate. So we just leave it to serendipity, actually, or what is it? I mean, it's not important that we control it. It can be go everywhere as long as we know the orientation and the baseline, just the distance between two antenna phase centers.
Okay, but I assume that we still need some type of active three-axis control to stabilize the spacecraft. If so,
yes.
Are you going to need propulsion? Because once we go to the moon, you have no magnetic field.
Yes, exactly. So propulsion is really needed, simply because you don't want to that satellites crash into each other. And if you have an arbitrary baseline, arbitrary attitude, yeah, it can happen. So there is some control needed. What you also don't want to have is that the whole satellite stumbling over again with a high speed. So you want to have some kind of stable, but not fully controlled orbit. So yes, you need propulsion, which is not a lot. We don't need to control it, like I said, but we need to have a certain amount of propulsion. Yeah.
A few questions about the ground-based observations. So you mentioned the scintillation problem due to ionospheric interference. Now, at visible wavelengths, this can be partially mitigated by adaptive optics. Is there a similar method for RF where you could essentially have a way of compensating for the phase?
That is possible. We do know that. I mean, if you recall that image made by the VLA at 74 megahertz, you need to do something with the data. What's done is a calibration, and we use calibrators, existing calibrators in space. So we just simply use known sources. So actually, what we do is we inform to a known source. We know what the outcome should be. We correct for that, and then we go to the source of interest and go back and forward the whole time.
Okay.
So that is our adaptive optics. Also on Earth, what you do is you made an artificial star to get information about that. We do that by using calibrators.
Okay. And I noticed in your presentation you also mentioned that you have multiple arrays throughout Europe. Now, is each array essentially an independent observatory, or do you actually combine all of them?
Both.
Okay.
So some science does not need long baselines and therefore very detailed information about the universe. And then a station can act as a standalone system. But the added value is to make a big array all over Europe. So what we do is that there's one organization, we call it the International LOVAR Telescope, the ILT, and that's the organization where all the countries are participating. And we decided that I think it's about 70% of the time is allocated for operations where all together, and we have the big telescope, and 30% is up to the countries to do their own independent research.
So for very long baseline applications, I imagine there are a lot of challenges in terms of synchronization.
Oh yeah, but there are even challenges on synchronization on local aperture arrays. So that means that we have rubidium clocks everywhere for clocking, and then we're even using other techniques along the line. So white rabbit techniques. I don't know if you're familiar with that. We have fibers between the stations, long fibers, and we use actually you calibrate the fiber to correct for phase differences between the individual stations. Yeah. Okay. But it all starts with clocking and frequency and time accuracy, and we're using rubidium clocks for that on each station.
Okay, sounds like quite a massive effort.
Oh yeah, it is.
Okay, we have a question from Mr. Liu. Thanks for introducing this impressive effort. I'm sorry if any of the questions below has already been mentioned. What is the budget scale of the CubeSat concept, and what would the expected lifetime be of the CubeSat experiment? On the technical side, how is the local oscillator signal controlled and transmitted? Thank you.
So the budget, it's I think towards €1 billion, 100 million, 1,000 million euros for the whole system. We don't have that at this moment, so we're aiming for a big ESA or perhaps even a joint ESA and another organization in the world, NASA, JAXA. We don't know yet. So, but we are aiming now for an ESA large proposal, which happens every 5 years, I think. So that's one budget one. For the small on the roadmap operations, yeah, they are much cheaper. And to give you an impression, the NCLA payload experiment was about 5 million euros, I think. So so that's also a lot of money, but doable in the sense of getting money from. Other question was the local oscillator. So that has to do with timing, and therefore we use atomic clocks, and we use the inter-satellite link to make a network where we reduce the error in timing from each of the individual satellites. It's the same technique we also use for VLBI on Earth. And we have individual clocks everywhere, and we use actual signals, calibrators again, known signals from outer space, known galaxies to calibrate the clocks themselves.
Okay, thank you. And I believe the final question was, what would be the ideal lifetime of the lunar CubeSat experiment?
A couple of years.
Okay, thank you very much. If there are no other questions, then thank you very much, Mark, for taking the time to introduce some very big questions and very big answers to us. Okay,
thank you very much. You're welcome.
Okay, and all the best with your new projects, and hopefully I look forward to hearing more about the cosmic dark ages.
Yeah, we will publish it for sure.
Okay.
Thank you. You're
all right.
welcome.
Thank you very much.